Hello, my name is Kirill Efimov. I will give a talk called Smallest Accepted Method for Subset Selection. This is a joint work with Vladimir Spokojny, and let's start. First of all, the model. We considered it's a standard linear Gaussian model with some known matrix psi of regressor, unknown parameter theta star, which we want to estimate, and a noise standard normal ID with known variance sigma. We will work a lot with subsets of the whole index sets from 1 to p, whereas p is the size of theta, and we will denote a subset by letter kappa. Also, we will use the union of two subsets, the complement of kappa in kappa prime, and also there is a natural partial order on the set of all subsets. We say that kappa prime is bigger than kappa if kappa prime includes kappa. We will consider only linear estimator of kappa star, so all our estimates will look like submatrix S kappa multiplied by the observed vector y. And let's start to build our smallest accepted method. What we want from this method? We want that the so-called good subsets of kappa, we say that subset is good if outside of this subset the signal is not significant. And we want from our procedure that such subsets accepted with high probability. So how can we do it? First of all, we need some test statistics. We used this one. If we have a given loss matrix W, and the test statistics is just the norm of differences of two estimator. And if we have these statistics, and we can define acceptance rule. We say that some subset kappa circ is accepted only if these statistics for all bigger models are bounded from above by some values z kappa kappa circ. How to define these values I will tell you later. Just think that we at this moment have some fixed numbers. And if we have all z, z kappa kappa circ for all pairs of subsets kappa and kappa circ, then we can apply our smallest accepted method. We just find all models which are accepted and choose the smallest one. Of course, because we have only partial order on the set of all subsets, it means that it is possible a situation when we have several minimal accepted models. And we can't compare them because they all intersect and one doesn't lie in another. So in this situation, when we have many small subsets, we just choose any one of them, and this will be our answer. So what we need now is to define critical values z kappa kappa circ. It can be done in many ways. We used the next one. First of all, we use the simple decomposition of our test statistics into stochastic part and into the bias part. And what will we do is just bound separately the stochastic part and then bound the bias part. And just for upper bound, use the sum of these two bounds. So first of all, we will bound the stochastic part. Suppose that for a given pair kappa kappa circ, we have some tail function z kappa kappa circ, which depends on some x, which is fixed from the beginning, just some number I used for computational experiments 6 is equal to 3. And this tail function have this property. So suppose this function is fixed. Then what we do in our smallest accepted method, we compare our kappa circ with all bigger models. So we will do multiple testing, and we want to spread this property for all biggest sets simultaneously. What I say is, what we will do, it also can be done in different ways. One of them is just change the argument of zeta kappa kappa circ by layers. We first consider all models kappa which are bigger than kappa circ on only one element, and change the argument x on q1 kappa circ to have this, this bound for the probability of union of these events. Here we have a new notation. M tau kappa circ is the set of all models bigger than kappa circ on not more than tau elements. Then, I can use mouse, I forgot. Then after we define Q1 kappa circ, we can define the next one, Q2 kappa circ. Now we can consider the sets of all models which bigger than kappa circ on one or two elements, and we increase the quantiles to have again epsilon minus x, and so on and so on. And by this procedure we can define all q till k kappa circ, where k is the maximum possible. So this is the main part of the method. And what do we need now is to bound the bias part. The bias part we bound by this value, where beta is some constant which controls the bias variance relation. For example, we want to have minimal risk estimation, we will take beta equal to 1. But you also can take beta equal to 0, everything will work. We just will have less constructive critical values z, so our selected set at the end will be just bigger. We will put more components inside it. Here p kappa kappa circ is just a variance of the stochastic part. So this is our method definition. And now we can formulate some theoretical properties of this procedure. First of all, we just formalize the notion of a good subset. We said at the beginning, we say that subset circ kappa circ is good if the bias outside this model kappa circ is not big enough to, so it's bounded by this value beta p kappa kappa circ. So this is the definition of a good model. So the bias outside the kappa circ doesn't increase very much. And the theorem claims that our smallest accepted procedure with critical values we defined just before will not reject the good models with a high probability, 1 minus epsilon minus x. The next property of our procedure is connected with the oracle choice kappa star. We define the oracle model as like in the smallest accepted method we did before. We just consider all good models and choose the smallest one. And for this oracle model, we have some oracle inequalities that claims that losses of estimated by oracle and by our smallest accepted method differs in the norm. The difference in the norm is bounded above by some value z kappa star, which is just maximum over this sum. The short review of the proof of this theorem. We just we can just say that we just use the triangle inequality. We consider the model kappa kappa star, and use the triangle inequality to bound this difference by this value. But as we don't know the kappa star, so we have to consider all kappa which are not bigger than the size of the kappa star. But as you can notice, to apply our smallest accepted procedure, we need to consider all possible subsets of our parameter theta. And this is a hard problem. And in general case, it's not clear how to do it in computable time for our procedure. But for one special case, it is possible. And I will show what changes in this special case. So in this case, we have a matrix psi equal to identity, also as matrix W also equal identity. And for simplicity, we set the variance to 1. And as you can see in this case, the stochastic part is just the sum of the signals which lies in kappa but not in kappa circ. And because as we can rewrite those the norm of W where theta 1 minus sinus theta 2 as sum of independent observation, it simplifies very much the whole construction. First of all, because this sum doesn't depend which kappa we choose. We just need to fix the number of yi in this sum. So our tail function will depend only on the size of kappa complement kappa prime. And the next result claims that if we have some model kappa which doesn't include in itself a lot of signal from kappa star, from the oracle model, then we will that the probability of the event that any of this model will be accepted is very small. So this result tells us that in our choice, a lot of the biggest part of the signal in kappa star we will include in our choice. That's the sense of this theorem. And just let's skip the proof. Yes, we just apply that if kappa is accepted model, then the bigger model, that then the test statistics, which is the norm of the difference, will be bounded by critical value z kappa union kappa star kappa, which is just the sum of these two values. Also, if we use the decomposition by into stochastic and bias part, then using triangle, then using the property that that norm of the sum of two values is bigger than difference of the norm, we will have this inequality for the same value. And as you can see, if we just put this difference here, we'll have that the norm of bias should be less or equal than z plus beta. It means 2z plus beta. But in theorem, we claim that for our kappa, the bias is bigger than this value. So this inequality is incompatible. So that means that we will not choose such model with high probability. But more clear and easy to understand corollary from this theorem claims that if in some subset of our oracle model we have enough big signal theta star, then the probability of the event that we will not choose any component of this subset is small. Also, if we apply just for the subset consisting of one element, then we have this condition on the one component of the oracle, how big it should be, so we select it with the high probability. And now we can illustrate this theorem, this corollary. Let me explain what is shown here. First of all, we have p equal 100. We have 100 signals. The value of this signal is shown by green line. So from 0 to 60, the signal decrease. From 3 sigma to 0. And then we have just 40 signals without any with mean 0, without any signal in it, just the noise. So then we look at the red line. It is shown in the probability we choose this signal number I. So as you can see, if we have bigger signal, then with the bigger probability we choose it, which is intuitive. But then we illustrate the corollary. So what is blue line? It is very hard to understand from the first time what is written here. It's written that if we look, for example, observation number 40, then the probability here is shown the probability we choose at least one signal from the set from 40 to 60. So just going to the left, we increased the sum signal inside the set of the oracle, and the probability increased very fast, what was shown in corollary. So again, the corollary. So we increase this value by going to the left, and the probability to skip all the signals from this subset is decreased very fast. And now let's discuss why in this case the computational will be not NP hard. First of all, just consider how we defined our values Q. This was just the definition of these values. As we already shown, the value z kappa kappa circ depends only on the difference between kappa and kappa circ. So it doesn't depend which exactly kappa we choose. We just need to fix the number of components it adds to kappa circ. And so then just split this union over all subsets which are bigger than on 1 or 2 or and so on k elements into k unions with fixed the number of additional elements. And then we have this value. And we want to maximize it. And I want to say that the maximum of this norm will be when we put into our kappa the maximal elements outside kappa circ. Then the norm will be maximum. So we don't need to consider all possible subsets. We just need to order our sample and just take the first k maximum elements. So it's decrease the computational cost, and it's now it is possible to calculate in not very much time. So, and just for k equal to 1, we have, when we defined the tail function z, we have this property, and when we tune our q, we have this inequality. And I wrote it just wanted to show you that this q is just to measure how much we need to increase the critical value to bound not just squared normal distribution standard, but the maximum of n of p minus k circ normal observations. So we need to increase to cover it from above with the same probability. That's just to understand to where this q come from. And this is just a picture of the behavior of this values q. So sorry, I didn't write wrote the axis. We have this model 40 observations, p equal to 14, and then we just and this will be the value of q01. This is q02, 03, and so on. So it's decreased very fast to the 0 because, for example, for the last component, there's no difference if we here cover the sum of squared normal distribution independent, but we consider the sum of all observations, or we just order them and again consider the sum of all elements. There is no difference, so the last q will be always 0. But from the beginning, the difference between the distribution of normal and maximum of several normal will be very high. That's why the first one is very big and then decrease.
Could you say, is it always that it's monotonously decreasing? Can you state the result that it decreases?
At this moment, I'm not sure that it always decreases.
Because you select the largest and one with the remaining, and then you look at the second largest and the third largest. So
intuitively it decreases, but if it will be always, I'm not 100% sure. So I think that's all. I just want to mention what can we do more for this smallest accepted procedure. We can first of all consider the case of the unknown noise variance and somehow to estimate it, or use, for example, bootstrap procedure to tune the parameters of our critical value z for our smallest accepted method. And also it just was asked, we want to understand how the behavior of our correction q. So it will be nice to have some theoretical bounds on these corrections, some precise. Of course, we can, for example, use Benferronti, but it will be too very root. And also, it is interesting to know the bounds, some good bound on the oracle in the oracle inequality, which bounds the difference of estimated by the oracle model and by our model. So I think that's all. Yes, we want to call it an agreement.
Because I mean, it's not a particular problem.
not for this problem, but similar. It was a problem
Applying this, in that situation, it's another question.
questions?